US Physics Olympiad, year 2015, USAPHO, final exam. Problem B1. This problem is divided into two parts. It is possible to solve these two parts independently, but they are not equally weighted. Part A. An ideal rocket, when empty of fuel, has a mass mr and will carry a mass of fuel mf. The fuel burns and is ejected with an exhaust speed of Ve relative to the rocket. The fuel burns at a constant mass rate for a total time Tb. Ignore gravity. Assume the rocket is far from any other body. Question 1. Determine an equation for the acceleration of the rocket as a function of time t in terms of any or all of t, mf, mr, ve, tb, and any relevant fundamental constants. Question 2. Assuming that the rocket starts from rest, determine the final speed of the rocket in terms of any or all of mf, mr, ve, tb, and any relevant fundamental constants. Part B. The ship starts out in a circular orbit around the Sun, very near the Earth, and has a goal of moving to a circular orbit around the Sun that is very close to Mars. It will make this transfer in an elliptical orbit, as shown in bold in the diagram below. This is accomplished with an initial velocity boost near the Earth, delta v1, and then a second velocity boost near Mars, delta v2. Assume that both of these boosts are from instantaneous impulses, and ignore mass changes in the rocket as well as gravitational attraction to Earth, to either Earth or Mars. Don't ignore the Sun. Assume that the Earth and Mars are both in circular orbits around the Sun of radii Re and Rm equal Re over alpha respectively. The orbital speeds are Ve and Vm respectively. First question. Derive an expression for the velocity boost delta v1 to change the orbit from circular to elliptical. Express your answer in terms of Ve and alpha. Second question. Derive an expression for the velocity boost delta v2 to change the orbit from elliptical to circular. Express your answer in terms of Ve and alpha. Third question. What is the angular separation between Earth and Mars as measured from the Sun at the time of launch, so that the rocket will start from Earth and arrive at Mars when it reaches the orbit of Mars? Express your answer in terms of alpha.